Hey everybody, it's Mr. Mott. What we're going to do is go through the sugar and salt solutions PHET activity. So we can, in this first screen, we can switch between sugar and salt. And some of the features we can do is look at conductivity. So I'm going to drag this conductivity meter in here and switch to sugar. And so start adding some sugar to it. And what we notice is that there's no conductivity with a sugar solution. All right. If I go to the top right, I can see the concentration. So I can see that as I'm adding solute and keeping the amount of water the same, the concentration goes up. Okay. If I remove the sugar and I want to test the conductivity of salt, add that in here, and guess what? We see the yellow lines kind of growing around our light bulb. So it is conductive. So something to think about is, why would these two things, which are pretty similar, they're white solids, why would salt be conductive and sugar not be conductive? Okay. One other thing that we can kind of explore here is how could we increase the concentration? Okay, so I could add more solute. Okay, or think about it, what else could we do? All right. And what we could do is that if we concentrated by removing some of the water here, so if I increase the evaporation, notice on the top right that the concentration goes up. And if I add more water, with keeping the amount of salt the same in there, so if I add water, the concentration is going to go down. Okay. If we look on the micro scale, we can kind of get a better idea about why sugar and salt act differently. So let's look at sucrose, which is a type of sugar, and we'll add some of that in here. So we add the sucrose in there, and it indeed dissolves, but you'll notice that the molecules really stay together. In comparison, if we add some sodium chloride, some table salt in there, the water molecules will actually separate the ions, and it's that separation of the ions that allows electricity to flow. And that's why a solution of sodium chloride or table salt will be conductive. Okay. Taking a look at a couple other chemicals here. So if I switch to, so I'm going to add a little bit of sodium chloride in here, and what you'll notice, there's a 1-to-1 ratio of the sodium ions and the chloride ions. The chloride ions being the greenish yellow ones there, and also the larger ones. If we, however, we look at the calcium chloride and we add those in there, we should notice a 2-to-1 ratio of the chloride ions compared to the calcium ions. Okay, so much more, twice as many of the greenish yellow ones there floating around. Okay, looking at, we can kind of compare sodium chloride again, add a couple of those in there to sodium nitrate. So those nitrate ions, those NO3s, we would hope to think that they would kind of stay together. So let's see if they are. So you can see some of these nitrate molecules floating around, 1 N and 3 O's, all connected still, floating around in the water. And that is the idea behind a polyatomic ion. Okay, they're sort of stuck together. Even though water separates the Na from the NO3, the NO3 remains intact. Okay. Lastly, we have two different sugars, okay, both covalently bonded. Okay, so that's sucrose, and we'll add in some glucose here. So very similar in terms of their chemical makeup. They're all nonmetals here, so they are covalently bonded, whereas when we had the ionic molecules, they were a metal and a nonmetal forming ions. Okay. To see what's going on, we can take a look at this really busy picture of water. And so we see the water molecules vibrating around. They've got some kinetic energy. And first we'll just take some sugar and drop it in there and see what happens. So the water molecules separated the sugar molecules there. However, the carbons and the hydrogens and the oxygens, they all remain sort of connected on a molecular scale. Okay. However, if we drop the salt in there, we'll see what happens. The water molecule separates the ions. And if we go to the bottom right and we show the partial charges, you'll notice around the positive sodium here, you have the negative part of water. Okay, sort of that's the driving force there. Okay, I'll drop some more salt in again. Let me actually turn on the charges again. And take a look now at the chloride ions. And the chloride ions are surrounded by the positive parts of water. And that's sort of the attractive force of the water sort of pulling apart the ions there. All right. So hopefully this has been instructive. Give you a nice visual of what happens, and you can understand and sort of go forward with what does dissolving mean when it comes to an ionic compound, and what does dissolving mean when it comes to a covalent compound, and how you can change concentrations as well. Thanks for watching.